Okay, welcome back, generals, to another Let's Fix It Generals at Zero to make the best game ever. We received a pull request on unassemblize from Baptista. He did some AI-generated suggestion, parallel processing for CPU-intensive operations. My first thought on this, it's a little bit too early to do this effort. I think first we need to lay out all the single-threaded work for the UI before we should start thinking about optimizing. Because if we optimize now, we make the logic more complicated. Because the threading logic will make things more complicated, naturally. Very likely. And then it becomes harder to refactor certain things. Right now, everything is single-threaded in the runner class. And if we now add the multi-threading, things become more complicated, and then it becomes harder to refactor things and move things around. So I'm inclined, just based on this already, to hold back most efforts going into threading direction. I think there are two ways that there are two approaches to threads. One is in the work queue to unclock the queue, because right now what happens is we have, let's make a visualization. So we have our UI threads. Let's just make a timeline here. So that's our UI, yeah, and that is one frame at a time, right? So we have frames, render frames, and we render the UI, yeah. And then next to it we have the work queue, which just runs beside the UI, and then from the UI frame we push commands, right? Push commands, and then here, like, we push a command here and here and here, and then this command takes a certain time to process until it's done, right? And so this command, in the meantime, it has to wait, and this as well. These commands have to wait, and so they can only kick off work when this is done. Then the next one can process. Eventually it's done here, and then the next one done, right? So we have here these three commands, and they all need to wait on to each other, because right now the work queue just works on one thread. So one optimization is here to have the work queue have a thread pool, and so that all these things, the work queue always runs and accepts commands. And then when we have a command coming in, then it pushes a command to a free job thread. So instead of doing this, let's make a new work queue. Here, that's our alternative. Let's call this WQ, and this is WQ2. And here we get the command 1, command 2, command 3. And it just like pushes it in on. We have here another thread, and these always run. These job threads, they wait for work, and it pushes it here, and it works. And this one pushes it right here, and it works. Pushes it here, and it works. And then so they can work in parallel, and then they can give back the results, and hopefully they can do it in a timely manner as to returning the result earlier here than here, right? So it would come sooner than this, right? So that's the first optimization. And the second one is that these these single commands themselves. So, well, we don't have much space here. MS Paint, beautiful, beautiful painting. Can we make this larger? Oh, it's hard to make it larger here. Okay, so let's say here we have this command, and then a single command could spawn multiple threads, right? And then they all do the work in parallel, and then once they are all done, they meet again together on one line and have one result, right? So there's these concepts. So we can have thread pools for runner commands and also thread pool for the work queue, right? These are two concepts. I'm more, for starters, I would be more inclined to focus on work queue parallelization. And then next step would be parallelization of the runner commands, and the command line would also benefit from this effort, but it wouldn't benefit from the work queue because it doesn't use a work queue. Yeah. Okay, so let's see what's in here. There's a space being added. Okay, execute the work. Spawn jobs for command to unclock the queue. Thread safety. Can we get more context here? Okay. Build match bundles. Yesterday we already determined that this function is not slow. Yeah. Okay, for this, I would first like to see, like, actually how slow is it actually, and how much do we gain for this? Like, just adding multi-threading just for having it, I think it makes no sense. We need to actually make a profile capture, see how slow it is, then make a capture with the thread pool, and then see how fast it is in comparison. Yeah. So this should be not just done entirely blindly. We need to know how long these things are. So I think before we start any parallelization, we should add some performance counters at various places that tell us how long certain pieces of work actually take, so we can see the biggest positions. And then the biggest positions, we then think about the best strategies to make them faster, right? Because just adding it here, I'm not convinced that this is the biggest CPU consumer, right? Okay, but other than this, let's see. Okay, disassembly function. This one could be an offender. I expect this to be reasonably expensive. But then again, here we need to, I actually want to work on this today, think about this stuff. But yeah, I think first we need to think about strategy for like breaking this into smaller tasks and not necessarily just running it on threads. Yeah. But yeah, in principle, there could be such a thing that, yeah, that we run all of these on threads and then have it fast. Yeah. Source lines, yeah, I mean, it accesses files. that's mostly bottleneck is disk access here. Parallelize per source files since they are independent. Future. Bit comparison record. What is actually SD future? I don't know what that is. SD future. Asynchronous operation can provide the SD future object to the creator. The creator can then use a variety of methods to query, wait for, or extract a value. Future. F3. Get a future. Task. Package task. Okay, I didn't even know that C++ has these things. Interesting. Huh. I wonder if that would have helped us in our work queue. Async, what is this? Huh. A city accumulate. City async launch. Okay, I first need to study how these things exactly work. I've never used std async. I never used shared future. Never future. Shit. How much stuff is in here? Okay, I know lock. I know mutex. I have no idea what these things are. Sleep, okay. Thread, okay. Condition variable, yeah. Semaphore. Ledge, no idea. Future. Okay, I'm lacking on the future. Hazard pointers, what the hell? What is coming up there? Jeez. Okay, atomic types is clear. Okay, so there's a bunch of atomics here. Atomic fetch. Okay, atomic fire. Okay, this future stuff. Let me see. Provides facilities to obtain values that are returned and to catch exceptions that are thrown by asynchronous tasks. Functions launched in separate threads. These values are communicated in a shared state in which the asynchronous task may write its return value or store an exception, and which may be examined, waited for, and otherwise manipulated by other threads that hold instances. Stores a value for asynchronous retrieval. Broken promise. It's never good to break promises. I don't know if that's true for programming. Transmit a result between threads. Accumulate promise. Promise get future. Work threads. Accumulate. Numbers. Future. We'll wait until the future has a valid result and retrieves it. Oof. Promise. Accumulate promise. Accumulate future. Future has a valid result. Work threads. Promise. Future. Okay, so you use this to get some state. Get state. Until the future has some values. Store value. Result or the exception? And how, like, where's the set to ready? When the thread finishes, or? Ah, here. Aha, okay. Set value. Yeah. I wonder if we could have used this approach for our work queue as well. In our work queue, I don't know. We do similar, yeah, but this, I don't know. Okay. Package task, what is that? Callable target, function lambda, by an expression that can be invoked asynchronously. Aha. Package task. The package task is a little bit like what we did with our delayed commands, right? Package task. Which we basically just put into a std function. So what is the difference between a package task and an std function? Ah, it can get a future. And then what? task lambda, package task, return. Package task. Okay, so you create a task which has like a function here. This task gives you a future. And you run the task here. And what does this do? Does this spawn a thread, or what does it do? Task. Okay, so you can run the task without threading. Here, this run in the threads. Okay, I see. Yeah, it allows you to do nice things. Async. Potentially in a separate thread. There's certainly something to keep in mind, these functions. Next time we use multi-threading, we should keep this stuff in mind. I actually didn't know that this existed. I never used it. Looks pretty useful that you can get a result automatically from a task. That's cool. Deferred invocation. Lazy evaluation. The first call. Okay, well, okay, it's C++ 23 feature. It seems to have really nice features. I don't fully understand all of this stuff, but I think it does a lot of things that we also try to do with our work queue. Yeah, okay, but I mean, the work queue we have right now, it works with what we need, so that's fine. Okay, let's get back here to then what this thing does. Okay, let's look at the thread pool. What does it do? There is a NQ, and that's it. NQ. Oh, what is this here? Why is it written like this? Why is it written like that? Auto return. No, 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 no. Okay, how do we start reviewing this? Oh boy. Okay, first we should hold off. We should hold off with multi-threading in runner class until all work functions. We should hold off with multi-threading in runner class until all work until all functions for UI commands, UI work commands are laid out. Define the static mutex. What? Okay. Okay, so this guy wants to start a future for every source. Let's see the future. Let's go back to the future. Waits for value that is set asynchronously. Full NQ. Where does it use the result thingy? Huh? Here. In Q. What the hell is this here? Ah, it's a lambda, right. Plus each source in parallel. Let's look at ThreadPool. Num threads. Workers. Q. Tasks. So this the thread pool also works as a queue, the way I understand it. You enqueue, but you don't dequeue. Num threads. It would be interesting. Hardware concurrency. Returns the number of concurrent threads supported by the implementation. Value should be considered only a hint. Yeah, okay. Num threads. Yeah. Okay. So it's how much is this actually created? Pool threads should probably perhaps account for UI threads that always needs to run as well, and for UI threads and work queue threads that always needs to run as well. Also pool should probably be a singleton somewhere. Otherwise, there could be competing thread pools from different calls. Okay, here we do not use exceptions unless some third party lib throws. We do not use exceptions unless some third party lib throws them, like cx opts. Looking for error. This is too much. Wait for all tasks to complete. Okay. Mutex. I don't like this approach here. I do not like this approach. These locks will contend heavily and put threads to sleep. Will contend and put threads to sleep. These locks will contend and put threads to sleep. Push and Q. Function name. Oh, it's also So I think it does it on every place, right? So the future is nothing other than a signal to this task is done. That's it. So instead of like waiting for threads to finish, this is all about waiting for the data, the task to finish. Okay. I mean, this is good in principle. In principle, I like the way the thread pool would be set up. It makes sense to me. But I don't like how this is implemented in the use case. Like, all these become singular tasks, but they are not so, like, there could be the case that the overhead from the tasking is more expensive than this whole work, you know. How expensive is this pushing and enqueuing in relation to the actual task? I think this needs to be measured in Profiler. It looks very... It is possible that the overhead exceeds the cost of the tasks minus the advantage from threading, from multi-threading. For these kind of batches, I would expect to give the tasks. I would expect to give the tasks a range, and then work on these ranges to then return a range result and then merge those range results in order. For big batches, I would expect to give the tasks a range to work on, and then I would expect to give the task a unique range to work on, to give each task a unique range to work on, and then return range results and merge those range results in order. Then merge those range results from the future. Merge those range results from the future in order without using any mutex. Yeah, so the problem I'm seeing here is this looks highly inefficient. Like the cost of this threading like could be super expensive. So the gain of the threads might not be as great as one would hope. So the cost, so let's say you have 8 threads here, yeah, and you do the work of that would have been done on a single thread on 8 threads. The benefit from these 8 threads might be just times 2 times 4 instead of times 8, because of this locking here and the fact that you enqueue every single task as a single thing. So you have this vector here, it's being pushed to, it's being allocated, it grows, it's not reserved, it always needs to be, yeah, it needs to be allocated once because this one is called once. Yeah, so it looks the implementation looks inefficient for what it wants to do. So it should be, we should do it better than this, I think. Yeah. Okay, but I see the AI tried its best. But I think it's not a good approach. I think it would be fine if this was like a really expensive thing, right? Then then this is justified. But this in itself, yeah, this looks rather cheap, right? You have some function IDs per source file. Yeah, this should be relatively cheap. Yeah, I don't know. I would have tried to implement it with ranges. Basically, let's say you have 8 threads, and you have 800 source files, yeah? Then you split those 800 source files in chunks of 100, and you give each task 100 of these. Now, there will be some unevenness, right? So maybe you could split it up in 16 times 50 or 32 times 25, maybe. Yeah, you can maybe make a bit smaller, but you don't need to have one task for just one file. You could have multiples, and then you let them all work, all these all these futures, all these tasks, and then you get the futures, and then you use the futures to assemble the final result. Yeah. The only problem is then, well, hold on. Pushback. No, the futures will be in order. Oh, that's good. Yeah. So here we go one source file, one after another, and we push back into this container. So the futures here at the end will also be in order. So we can process the results in order. Yeah. Yeah. So I think this can be improved, but I think it's going into the right direction, but it's not there yet. And probably the same here. Like this is probably also highly inefficient. It's this accounts to all use cases. Yeah. Let's edit. That needs to be running well as well. So, for example, pool count may have to be -2. Maybe. Build match bundles. Huh? I also wonder, is this lock really necessary? Matches. I'm not sure if this lock is even necessary, because source. Well, I'm not sure. Is this lock even necessary? There should only ever be one function to one set of source lines. No? I wonder if it's even possible for this to compete anywhere. But maybe I'm missing something out, because I think that if you have a source file and you look at its, yeah, you look at one source file and it has a, well, what about inlines? I'm not sure. Maybe inline functions? Perhaps can raise, but no, inline. I'm not sure. Probably would need some testing, and you could put like atomic value into this and see if it's only accessed on one thread. Could be tested with atomic counter to see if it is accessed more than once. Yeah, so basically put a atomic counter in here, increment it, and if it's 2, then you know that more than once accesses it. But I think it's just 1 max. I could be wrong. It's always better to test. Yeah. Oh boy. Yeah. I mean, in principle, it's not bad, the thread pool, but there need to be a bunch of changes. But I do like the idea with the future. That's good. Yeah. That's not bad. Okay, let's look at the thread pool. Stop. Make share, package task. Oof. It's a lot of F. It's a functor. Please do not return auto. Tasks. It is a bit. It is sad that we Well, sad is a bad word. It is unfortunate that this function takes it's unfortunate that this function can we return tasks? And place task. How do we make a, like, I'm wondering, does it mean that the future can only ever be void? Can the future only be void, or can it also return some nice data? Can the future only be void, or can it also return some data with this ThreadPool? Workers and place back. Task empty. Unique log. Okay, so this thing simply allows to push in queue a task, and some worker will pick it up here at random. Yeah. Mm-hmm. Yeah. I guess, I mean, the thread pool in itself is not bad. It's super simple. So I guess it's good. Worker.join. I think stop and join should be decoupled into separate functions for finer control. But still be called in this destructor. I think the way it's written like this is because maybe because in the return type it cannot type this here. I'm not sure. Let's change this. Can the return type be written without auto? Stop. Throw. No exceptions. Make enqueue return bool instead. Yeah. Yeah, I think it's going into the right direction, certainly. Another suggestion here, instead of asking, instead of using AI generated thread pool, pull one pull an open source thread pool from GitHub. Instead of using a original thread, perhaps pull an open source thread pool from GitHub. Pull a high performance open source thread pool from GitHub. Here also, this comment is still relevant. The queue essentially needs to push command work to a thread pool, to a global thread pool. Note that there needs to be care if trying to use ThreadPool from within, to use a global thread pool from within a thread of the global thread pool is currently not the case. But we also, there needs to be care, but also we cannot just have chains of thread pools. So so we need a suitable strategy here. So for example, a small thread pool for example, a small thread pool for the work queue and a large thread pool for runner. The larger, for example, one small thread pool for the work queue and a larger thread pool for the runner. Cannot just chains of large thread pools. Perhaps for starters can have one small thread pool for the work queue and a larger thread pool for the runner. Yeah. Cancel. Okay. Okay, but I think this comment here, this takes precedence. Hold off from multi-threading in runner class until all functions for UI work commands are laid out. But I think for the work queue, this can already be explored, I think. Let's put that as well here at the top comments. But for the work queue, we can already explore the thread pool. Already explore and test the thread pool. Okay, so these are my thoughts on the high level stuff that I see here. I didn't look at everything in all detail. I also didn't fully understand the thread pool. Like I didn't look closely if all these conditions here make sense. But like in a nutshell, it looks like things make sense. Like, well, things could be optimized here. So for example, this could be more efficient by resizing M workers before filling, right? But there, these are small things. Auto task. Yeah, I don't know if this lock here is necessary. Because in place. Yeah, I guess it's necessary. Yeah. So this is also then. Wait, task in place. And here it also takes the lock. Yeah, okay, so this is also unique lock. What is this? Unique lock. It is a mutex, yeah. Unique lock takes mutex, yeah. So this is also contending. Condition wait lock. Okay, so it will, if there is one element in the queue, it will wake one of the threads that gets to work. And if there still is something left in the queue, then it will wake another thread and so on until all the threads are busy. And then, okay, this is probably fine. Yeah. Yeah. Yeah, it goes into the right direction, but it's not quite there, I would say. Let's add comments. Good. What's the time? Oof, 1 hour 30 just on this review. Good. I will take a break now, and after the break, next session we will continue with this here. Disassemble function matches, and yeah, to get our runner commands in order so that we can use it in the UI. Okay, then I will take a break here. I wish you a great day or night. Until next time, goodbye.